Okay, welcome back, everybody. Can everybody hear me well? Is the sound in the room okay? Can you hear well? So sometimes I have to get the microphone closer to my mouth here. Sometimes I tend to mumble. So let me know if there's any problem with the sound. Feel also free to get closer here. So I'm still using a cable. I'm not running it in a wireless way. So I will, when I go back and forth between the laptop, I will stand over there. So what I'm going to do is to do a little bit repeat of some of the messages which I gave you on Monday. And then we're actually going to repeat, and you will see that there are many things you've seen before. We are going to remind ourselves about Newton's law and things like that. And a very, very simple case like a falling object in one dimension, which you probably have solved in physics 181, for instance, just as an example. And slowly, we are going to link things up with the coming assignment. So on Friday, we will basically use our time to discuss and solve the first assignment. And we are going to run these classes in a semi kind of flipped classroom. But today is going to be Mondays and Wednesdays are mainly going to be dedicated more to lecture type of form. And Fridays will be the sessions when we're going to float around here and discuss the solution of the assignments. So I hope that's a modality which fits well. I also wanted to remind you of a form which I sent out as an email to you in case you would like to team up with people and solve the weekly assignments. So I see that many of you already are sitting together, so maybe you would like to collaborate. You can hand in one common assignment if you want to, or you can hand in your individual one. But remember that if you don't do anything in D2L, if you don't hand it in, even if you collaborated, you actually need to hand in an individual assignment, because else your name will not appear in D2L. So if you collaborated and one of you hands it in and you are free together, it's only the one who handed it in who will appear for us when we are grading and putting the score in D2L. So just remember that. That is just a gritty-nitty detail with D2L, because we won't see your name if you don't upload anything. Okay, so just a quick reminder of where you can find a lot of the material. So I'm using GitHub, and I can see that many of you actually are pretty familiar with that. It means that you can, if you click on code here, you can clone everything down to your laptops. You can fork it if you want to. And if you do that, you can keep editing on it. You can push it to your own GitHub repository and just use this as your material. So you will find Jupyter notebooks of every weekly slides, the homeworks, everything. You will find that in different types of formats, and the Jupyter notebook is just one of the formats. And you can use these when you solve your exercises. When you solve the exercises, there is obviously a handwritten part. The easiest way to deal with that, if you don't want to type everything in LaTeX, for instance, which is a mathematically typesetting language, the easiest way is just a handwritten piece of paper, and then you just use your cell phone and you use that one as a scanner. Actually, the cell phones which you guys have are actually much better than many scanners. So you can just take a picture of your different papers you've written and then just upload them to D2L as your answer. And then there is a Jupyter notebook, which is a numerical exercise. And then you would typically hand that in as a Jupyter notebook. If you're familiar with typesetting mathematics, you can obviously write everything as a Jupyter notebook. That's fully possible. There's no problem with that. It takes a little bit more time. So if you're a little bit stressed, I mean, a scanned version of your paper and pencil answer is perfect, as long as we can read your handwriting. That's the obvious limit. So I also wanted to say that if you look into the GitHub folder, you will find there's a doc folder here. And here you will find, if you go to literature, you will find the PDF of the textbook by Taylor, which is a very good textbook. And I normally recommend using that one. And I will send you weekly reading assignments before the week begins. So take a look at the textbook. If you like it, feel free to buy it. It's a little bit more on the expensive side, as I said on Monday, but it's a very good textbook. The handwritten notes from every lecture which we have, they will typically be posted here. So if you click on Spring 23, you will see now at Spring 23, you have the handwritten notes from Monday. And they will just keep popping up after the lectures. The videos, as you've probably seen from D2L, is also available right after the lectures. And normally it takes roughly 10 to 12 hours for YouTube to generate the subtitles. So YouTube has actually invested, or Google has actually invested a fortune on machine learning algorithms to recognize speech. And it does really an excellent job. And if you are not, if English is not your language, you can actually translate the subtitles into, I think it does it automatically in 12 other languages. And it does actually a pretty good job. So I don't do any editing of the subtitles simply because I'm lazy. It takes time to edit subtitles, but normally it does a pretty good job. But you will see some glitches here and there. Like the physicist Feynman is sometimes translated into fireman. So these are things which happen. So just be patient with that. Okay, so that was a little bit about more technicalities. The weekly slides are those which you will find posted here. So if you go into the different weeks, you will find the material we aim at covering. So often there is more material than we will have time to cover. The exercises, you will also find them at the bottom here. So if you scroll down on that page, you will find links to the weekly assignments and the midterms and the final. So if you just scroll down a little bit here, you will find the first exercise set. You can, if you want to teach yourself LaTeX, if you haven't used it, you can actually use the file which is here. And you can just use this typing and just, that's the way I actually was taught using LaTeX, was a kind of monkey see, monkey do. You got an example and you just kept repeating what was in the example, and then gradually you just pick up new things. But you can also see that's a Jupyter notebook, which is the basic exercise set. And you can use that one as a starting point for solving the homeworks or the midterms or the final one. So just to remind you, the midterms are in the form of take-home exams. So we roughly have 1 week to 10 days. And the same with the final. So we don't have a final sit-in-person final, but you will roughly get a week to solve the final exam. And it's going to follow very much the same pattern as we had in the midterms and the weekly assignments. Every weekly assignment has a numerical exercise, so that gradually we are going to baby step you through the course here, so that with the different programs you write every week, you can reuse them in the next homework, in the next one, in the next one, and you can keep building up on it. And as you will see, when we solve many problems in mechanics, it's actually you solving differential equations. From a programming point of view, that means that you will be triggered, or your physics insight is the one we want to trigger, because if you can find the forces which are acting on the system, you can then find the acceleration. And with the acceleration, you can set up the numerical solver. So actually, when you have written a program to solve numerically a differential set of equations, the only thing you will need to change from one assignment to the next one is actually the forces at play. And that's where we think that this is a way which can trigger physics insights, in the sense that we will focus more on you finding the forces and understanding the physics of the system, rather than going through many mathematical tricks to solve equations. Mathematical tricks are very, very useful, but they can often take away the attention from the physics itself. And in a way, this course is to have you start thinking as physicists. And hopefully this is a way by which can trigger a deeper insight. This is what we hope, obviously. We may not succeed. Okay, any questions so far? Because I'm going to switch pretty soon to the whiteboard, and we need to go through some technicalities so that we can also look at the exercises in a more meaningful way and also prepare ourselves for next week. No questions? Everything clear? Okay, so I'm going to switch over to the whiteboard here, if that's okay. And feel free to answer the questionnaire in case you would like to team up with people for solving the weekly assignments and the midterms and so on. So what we normally done is to try to put people together, depending on your interests, so that we can have teams which hopefully function well. If you already have some teammates, I mean, there's no need to fill in the form. Yeah. I just have to take this one off because it, yeah.
Did the teams change throughout the semester?
So it happens that teams may not function. And then this is very much up to you, but we hope that putting together people, it will function, but there's no guarantee, right? So we've had only in the last 2 years during COVID, I think we had only one case when the team just broke apart. So normally it functions pretty well. And it's a good way to get to know people. Okay, so let me switch to the whiteboard here. I'm sorry for repeating many of these things, but it's always like this in the very beginning. So what I'm going to do now is to bring up some of the definitions which we are going to need for solving exercises. And one of the things which you will meet is the need to define an origin. And on Monday, we discussed whether the origin should affect the outcome of a physics calculation. And then we all agreed that the origin should not affect the output of a physics calculation. So if the energy is a quantity we are calculating, the final energy should not depend on what kind of origin we have chosen, or whether we have a frame which is being rotated or whatever. So there are specific quantities which are always conserved. So one of the things which we will have to deal with is actually to choose an origin. So let's just write this down here. And if we are in 2 dimensions, since we will deal with vectors, we will always rephrase this in terms of a vector. So suppose this is the x-axis and this is the y-axis. You have 0 here, 1, 2, 3, 4. I can still count, guys. And if we have a point here, this will be a point P, and we will typically label that in terms of an x and y here. Alternatively, if we are in 3 dimensions, and if we insist on a Cartesian system, as you can see here, I've chosen a Cartesian reference frame. I have chosen an origin, and this point here is now defined in terms of a specific origin here. If I move to 3 dimensions, and this is where it gets difficult for me, I am a very low dimensional person. According to my wife, I just live in 1 dimension. But so when I venture into 2 and 3 dimensions, I am on a shaky ground, guys. But let's see if I can make something meaningful there. So we can have the x-axis, we have the z-axis, and then we have the y-axis. And we would typically define unit vectors. So this would be a vector which we would call EZ. And you will see that this has actually different notations in different textbooks. So some textbooks would write it like an E3. So I'm putting vector signs, or you will see this written in terms of the symbol K. And you may even experience that some textbooks, they are not consistent with the notation. So in a textbook by Taylor, they use the letters I, J, K, and I will try to be consistent. If I'm not consistent, let me know. But I'm putting up these different ways of defining it. So we would have a unit vector here in the X direction, and some authors would write it as an E of X. It would be written as an E of 1, or just as a vector I here. And finally, we would have a vector in the Y direction. So this would be an E of Y, which could often be written as E2, or just as a vector J here. I guess you've seen this kind of notation before. So I hope you don't get offended again if I repeat too much here. So we would have a new point, and this point is defined by X, Y, and Z. We are looking at the Cartesian system. And that specific object, if we now think of this as a vector, we could now think of this as a vector A, which is now given in terms of the coordinates X, Y, and Z. So that specific point, which we have picked here. Then this is something which you would write out as a component X times this vector Y, no, I in the X direction, the unit vector. We have a component Y multiplied with a vector in the J direction, the unit vector, plus the component C times the unit vector in the Z direction. And the thing which is important for us now is that these objects, they have a unit length equal to 1. They are orthogonal. So if I take I times J, this is equal to 0. And this is the same as I times K is also equal to 0. And this is the same as J times K here. And this is equal to the absolute value of J and the absolute value of K. Now, if you look at one of the exercises which we have, so if you look at exercise 3 for this week's assignment, so this is exercise 3, you actually ask to prove. So sometimes when we write prove, we often also mean show. And one of the things you have to show is that the vector A times B plus C. So you have this kind of mathematical operations here, which are very useful for us when we are going to do physics. So this is one of the things you can show. I know that many of you have not had linear algebra. Is that correct? Not everybody has done linear algebra. Because if you're familiar with linear algebra, you could actually set up the vectors as you would do in linear algebra and simply perform the calculation of two vectors that way. But the way you would do it now, if you just limit ourselves to 2 dimensions, and that's enough for the exercise. You don't need to do this in 3 dimensions. 2 dimensions is enough. So if you stay in 2 dimensions, if you look at the first term, so if you just take A, I mean this specific term here, and plus this one, so you would have a vector AX times I plus AY times J. And this is now multiplied with B of X times I plus B of Y times J plus CX times I plus CY times J. And what you need then when you're multiplying out things is simply to look at AX times I. When you multiply this one with this quantity here, then you know that I times I is equal to 1, right? But if I multiply I with J, that's equal to 0. If I multiply J with I here, that's equal to 0, and so on. So what you need to do then is simply to use these relations which you have here, and obviously that these vectors are unit vectors. And when you do that, what you will get then is obviously the following. You will get an AX times B of X plus an AY times B of Y plus AX times C of X plus an AY times C of Y. And when you collect these together, you can actually rewrite this in terms of vector A times B, which would be the term which you see here, plus A times C here, which is then the terms which you have here, which lead to this term here. So sometimes don't feel intimidated when the text says prove, because often that means show. So this is the way you would typically solve this exercise. And then there are other relations which are important for us. So one is the curl, which is a very important quantity, mathematical quantity. There is also the derivative of vector multiplied with another vector, which also quantity which we will need. So this first assignment which we have deals a lot with mathematics, which you may have seen and perhaps forgotten, which we will see again throughout the course here. So like the first exercise with exponential functions and cosines and sines are things which we're going to look at when we are studying harmonic oscillations, for instance. Is the voice okay, everybody? No corners here? Goodie. So let me go back a little bit to one of the other things which we discussed on Monday. So this is about the vectors, the representation of vectors. And then we had something which we called dimensions and units. Dimensions, scales, and units. And this is also something which becomes important for us when we are going to solve equations. And I will try to motivate why. So there is a, if we look at the quantity R, which I'm going to call distance in generic terms, the dimension of that is normally indicated by these bracketed brackets. This has dimension length. We also define time, t. So this is the kind of labels which we are going to use for these quantities. So t has obviously dimension time, velocity, v, and we are going to indicate that as a vector. And if you don't see a vector sign, that means that we are in one dimension, and then this quantity is just a scalar. Okay, so if I don't put vector signs on it, then we are just dealing with a one-dimensional system. So this is velocity, and velocity has obviously dimension length over time. We defined acceleration, and acceleration has length over time squared. Another quantity which we are going to use repeatedly is actually the force, and that is mass times length divided by time squared, or over time squared. So that's the dimension of force. Now, I will bring in other quantities later, like the potential energy and the kinetic energy, which we are going to encounter a little bit later. But let us now remind ourselves about the Newton's law and some specific cases which we are going to study a little bit later. So if we look at F, so we are going to live in one dimension now. So that means that we have, for instance, just f of x, or just f. And that's going to be equal to m times a of x, or just m times a. So if you don't see any vector sign, this is just a scalar in one dimension. Now, typically, one of the things which we are going to look at is to identify the forces. We would divide by mass, and then we obviously have the acceleration. So in this specific case, we are just looking at a one-dimensional case. So that is F divided by m, which is equal to a. So this is Newton's second law. I assume you have seen that before, but we are going to pick up these things gradually when we move on here. Now, this is also written in terms of the derivative of the acceleration. So that means that we have a dv of dt. So that's the acceleration. And this is again the same as the second derivative of the position with respect to time. And we would write this as a d of dt. And then that is a mathematical operation. And then we have the derivative with respect to time here. So I just wanted to bring up an important thing when you look at this and you're doing a dimensional analysis. So note well here that you have time here. So this is 1 over time. This is 1 over time. And this is length. And when you do the dimensional analysis here, you see that this is length divided by time squared, which is the dimensionality of acceleration as we decided or as we defined it here. So this is the instantaneous change of velocity as a function of time. That's the way we define acceleration. So clearly, if you have a constant velocity, then the acceleration is equal to 0. If we now look at these types of equations, it's common when we are solving the type of equations to make one of the variables dimensionless. So it's common to introduce dimensionless variables, and that can often simplify the mathematics which we are dealing with. So it's common to introduce dimensionless variables. And then what you would do then is simply to multiply your final results with the constants which you have introduced. And remember again that when we are going to deal with, let's say, time, you may have something which depends on a cosine and has time as argument. You cannot take time or cosine of something which has a dimension. What does it mean to take cosine of seconds, right? So the argument to a function is always dimensionless. That's something to think of. So when you take an exponential and you have an argument, that has to be dimensionless. So that means that often when we rewrite the equations, this sounds again like a boring technicality, we will often transform them into dimensionless equations. This is also useful because then equations which look very different, they can suddenly look the same. And the only thing which will distinguish them would just be some constants which we multiply the final answer with. So actually, when you're going to write a program for a harmonic oscillator, if you change velocity and position with electric current and resistance, you can solve this with the same differential equations. You can solve a problem of a circuit which is called an RLC circuit, which has a capacitance, an inductance, and a resistance. And the equations are going to look the same when you scale them properly. So that means you can reuse many of the things you do in this course in other physics courses. So that allows you to see the more kind of generality behind solving a specific problem. So you will see examples of this many, many times here. So a typical thing you would do is to introduce a dimensionless time. So that means that your time is now given by some dimensionless quantity tau divided by alpha. And this parameter alpha should then have, this is just a constant which we choose, that should have dimension 1 over time. And then you see that when you bring that back, you get the proper dimension. So tau is dimensionless time. So if we go back to the acceleration, where we have F divided by M, so it's pretty common actually to write the acceleration in terms of the forces. So you're going to analyze a problem, you will find the forces, and then you divide by the mass, and then you get the acceleration, and that's what you will plug in the numerical solution of a problem. But you need to find the forces first. So this would then typically now be given by this second derivative with respect to time. So we have a dx dt, and now we introduce this dimensionless time. So we have assumed that this constant alpha is a constant which we know. we don't need to specify it now. So what you would get then would be a d, and then you have a d of tau over alpha, and then you have the d of x and d of tau over alpha, and we can put alpha away. So we would multiply with alpha on both sides of the equation. So we can actually rewrite this as f divided by m and alpha squared. And this is now equal to d of d tau. And this is the second derivative. And we have a d of x of d tau. Okay, so this is one way by which we would scale the equations, and we get rid of some specific constants. So if you look at this equation here, what is the dimensionality now of the problem? So if you want to make a dimensional analysis, which dimension have we in this specific case? So previously we had length divided by time squared. That's the dimension of acceleration. So if you look at the equation here, what's the dimension of the problem now? Say it again. Just length. Excellent. So what we have now is just, we've gotten rid of time as a specific quantity. We have dimensionless time. So the left-hand side and the right-hand side, they have just dimension length. So these things are actually very important to think of, because it's very easy when you're plugging in the correct units to put in the wrong units. Are you familiar with the Voyager from '99, which was supposed to pass Mars? And why it didn't hit Mars? Has anyone, yeah? Yes. So they mixed up metric system with imperial units, and bye-bye to millions of dollars. And this had to do with a small error inside the programs, where people actually forgotten about this. So you write the equation in a specific way, but then you have to remember to be consistent with the type of units and the type of dimensions you're dealing with. And you will be shocked to see how many such stupid errors we humans have made and keep making, because we don't pay attention to these things. So this is also very useful when we analyze a physics problem. As I said, it doesn't sound like a very exciting topic, but it's actually very important, because at the end, in this course, you actually have to analyze what the results mean. And then you have to have a feeling of what kind of quantities you're actually calculating and what they mean, and whether these quantities make sense or not. And that's your job, actually. Okay, so let's continue a little bit. Let's take another example. And this is about the gravitational force. And we are coming back to this. And you've probably seen it. So the force between two objects at positions R1 and R2. So this could be two planets, as an example. That's given by the gravitational constant times the mass of one object times the mass of the other one, divided by the square root of the relative distance squared. So let me just write down this quantity R1 minus R2, what it actually means if you haven't seen it before. So this is the same as the difference between the x coordinates between the two objects plus the y coordinates plus the z coordinates if you are in 3 dimensions. So this is how to say, the famous force which Newton deduced. We are coming back to the derivations of this, or actually how this is inferred. If you want to read a little bit about it in a more popular science way, there is a fantastic small gem by Richard Feynman, which is called The Character of Physical Law. And he actually goes through in this text the kind of philosophical and mathematical reasoning which led to this expression here. And this is seen as one of the fundamental laws of nature. This is a gravitational force. And it has a very simple mathematical expression. And till now, there are not many experiments which actually break with this law, actually in the range of classical mechanics. If you're dealing with quantum mechanics, you would have to add refinements. If you're looking at relativity effects, you would have to add refinements. But this is a very important law in science. One thing you notice here is that this force does not depend on velocity. It does not depend on time. This is going to lead to a very important concept, which we are going to study later, about energy conserving forces. So this is an example of an energy conserving force. So if you see a force which depends only on the positions, then that's an example of an energy conserving force, often. We are coming back to this. I'm just anticipating things. The other thing which you see is that the force depends on the relative distance. And many forces in nature, we are going to meet, for instance, the Coulomb force, depends also on the relative distance between two objects. The strong force depends also on the relative distance between objects. That means also that this leads to specific symmetries, which we are going to study. So one symmetry which this leads to is what's called translational invariance. That is going to mean that momentum is conserved. Another symmetry is actually rotational symmetry, and that means that angular momentum is going to be a conserved quantity. So based on the form of the forces, we can actually derive many interesting quantities which are extremely useful when we analyze a physics problem. Now, if you look at the scale of this equation here, what often happens is that people, when they deal with this numerically, or when you're solving it analytically, is actually to take away some of the constants. And one of the constants you would take away is the gravitational constant. Does anyone remember the value of it? Fantastic. If you're stranded on a remote island, the only thing you need in life is a table of physical constants. That will save your day. I'm just a physics geek, okay? I just love what I'm doing. Thanks. That's good to see that people remember some of the concepts. Okay, so one of the things which you will see now, if we look at the force which we have, and you look at the dimension of it, if you do a dimensional analysis, this is the same as mass times length divided by time squared. That's the definition of the dimension of a force. And if we now look at what we have this constant minus g, which we haven't defined yet. And we have mass times mass. And in the denominator, what we have is just length squared. So if we now want to equate these two equations, that simply means that this constant g must have a dimension which is now given by length cubed divided by mass and time squared. So in order for us to get back to mass times length divided by time squared, this constant g must have this dimension. So this is often useful if you want to infer the kind of mathematical quantities which would enter the definition of a given constant or a variable in the theory. So this was just a small digression. So what we are going to do now is to get started with one of the first examples, the physics examples, a very exciting one, a falling object in one dimension. You've probably seen that zillions of times, but we're going to go through that one because this is related to one of the next exercises which will come. So let's look at or revisit an example which you have seen before. So let's specialize to one dimension, one dim, and an object which is falling in one dimension. And suppose somebody gives us the mathematical relation. So gives us that y as a function of time, the position of this object is given by some initial time, the position at an initial time, the initial value, minus 1/2. So we're assuming that there is no air resistance, there is no friction, no whatever. So this is just an object which falls in vacuum. And we know this quantity here. This is the constant of gravity, which should be 9.886980,665 meters per second squared. If we use these units, this is the initial position. And we would typically rewrite this as a yt of 0 over as a y0. So this is a kind of notation which I'm going to use again and again. Now, the thing which is interesting for us now, when we look at this, if we now plot this as a function of time and position, so we have time on the x-axis, and we have the position here. So we have y0 at a time t0, which is this one. And it's pretty common to choose time t0 equal to 0. So 0 seconds. That's a pretty common choice. Then we know that this object sooner or later is going to hit the ground here at a time t final. And this is a quantity which we can find easily. So we have that y of t final. And now we're assuming that this is equal to 0 meters. And this is obviously given by y0 minus 1/2 of g of t final squared. And then we can find the expression for t final by simply reordering this equation here. So that is going to be given by 2 times y0 divided by g. So that's when we are going to implement these things numerically, we would typically ask a question, make a simulation till this object hits the ground. And then clearly you have to figure out what is the final time depending on the type of problem you have here. So from here, when you make a simulation, you will start with time 0, and then you would run your simulation till this final time. And that would set up the time interval which you will need in order to solve this specific problem here. But let's look at this in a slightly different way now and see what kind of quantities we get for the velocities and what we get for the acceleration. And then we are going to go the other way around, and we are going to start with the forces, and then we are going to integrate up. So what we do now first is to take the derivative, because if we take the derivative of position, we get the velocity. And with that, we get the acceleration. Now, if somebody gives you the acceleration, then you can integrate up again, and you can find this expression which we have here. So what I said now is simply that this position is something somebody gave us. So let's go through these different mathematical operations and actually derive that equation there by going back again. And this is the last thing we're going to do today. So if we now look at the derivative, we know that the velocity as a function of time is simply given by dy dt. So we take the derivative with respect to time, and then we have the expression up here. No, I didn't. Where did I put it? Here we have it. Here we have the expression. Take the derivative here. And with that expression, what we get then is simply minus g times t. So we have a minus sign here because we are looking at an object which is falling down. And we have defined an origin, remember that. And now we are looking at something which falls down. And it's just in one dimension. And then we know that the acceleration is actually given by dv dt. So that means that we are simply getting minus g. Now, you've probably seen this many times. So we can now derive this equation for y of t from a of t. And the typical way which we are going to proceed in this course is that you are going to identify the forces first. That is where you are going to use your insight about the problem, and you're going to find what kind of forces is influencing the motion of a given object. So mechanics is a deterministic field, which essentially deals with you solving an equation of motion, and the equation of motion is Newton's law. You find the acceleration, you integrate up, you get the velocity, and then you can predict the velocity of this system over time. And when you have the velocity, you integrate up again, and you get the position. So mechanics deals essentially with this. It sounds very simple in the beginning, but many of the physics problems are a little bit more convoluted. But the basic message is actually this. We need to identify the forces. With the forces, we have the acceleration, and then we can integrate up. Wisdom one, if you can integrate analytically, you integrate analytically. There is no reason, if you can solve things analytically, to actually write a code for doing that. Many of the problems we face cannot be solved analytically. And then we have to integrate numerically or solve differential equations. And in a way, this is the kind of things we are going to go through in different disguises throughout the semester in this course. And we're going to look at different physics problems. So hopefully then doing this kind of things again and again allows you to be able to analyze a physics problem, perhaps in a better way than you were used to do before. So let's do this final thing here. So when we have the force, so suppose now we have analyzed the problem and we have found the forces, we divide by mass, we use Newton's law, and we find A of t. In our case, we are just in one dimension. So F over m is simply minus g, right? But just a constant, A of t. So this is an object which is falling freely, and there is no air resistance, no nothing. And I guess you've seen this expression before, right? So this is now the force at play for this specific case. And then we simply rewrite this in terms of the velocity. So this is now given by dv dt. And now we integrate. So in the previous case, we took the derivative. Now we take the reverse operation and we integrate. So we would now integrate from t0, which we normally put to 0, to a new time. And we have minus g here. And now I'm going to put the time t prime. And this is equal to the integral from t0 to t of dt of dv of t prime here. So I put a prime quantity because it's not the same as the final time. So t here is just t prime is a dummy variable, which I use in the integration. And we know that the term which we have here is going to be on the left-hand side, on the right-hand side. I still have problems with left and right here. So the right-hand side. This is the right-hand side of the equation. Sorry, guys. And we would rewrite this as a v of t minus v0. And since we've chosen t0 equal to 0, if I take the other expression on the left-hand side, what we get then is simply minus g times t. So that means that our velocity, v of t, is equal to v0 minus g times t. Now, if we choose the initial velocity to be 0, then we are back to the equation which we had before. So this is just a constant, the initial velocity. But when we are going to solve the problem, we have to be pretty picky about the initial conditions. So you will get a general solution to the problem, but then the initial conditions are those which really specify your specific problem. So I'm just leaving it. So you see now, this is exactly what we had before. We had minus g times t plus a constant. And then if we want the position, we integrate again. And this is where we are going to end today. And if we now look at the position, we know that the dy of dt is actually equal to v of t. And then we integrate again. So we integrate from t0 to t here. And then we have a d, a y, dt prime, and then dt. And we do the same with the velocity, which is v0 minus g times t prime of dt prime. And then we have from t0 to t. And we put this t0 equal to 0. So this is going to be equal, the left-hand side is going to be equal to y of t minus this quantity y0. And this is, and now I'm just going to be a little bit lazy. So I'm just going to put v0, 0 initial velocity. This is simply going to be given by minus a half times g times t squared, which then means that y of t is equal to y0 minus 1/2 times g of t squared. And that was the equation we started with. So somebody just gave us this equation. But the typical process which we will use is a process where we find the forces. When you have the forces, you integrate up, you find the position, and then you find the velocity as well. And essentially, what you see conveyed in this very, very simple example, which you probably have seen many times, this is the essence of what we are going to do again and again here, either by paper and pencil analytically or numerically. Any questions so far? I hope this wasn't too boring. It's just more to set the scene for what is coming. Any questions, guys? Okay, if you wish to hang around, because I have office hours after the lecture, if you wish to hang around, you can do that. Ask questions, whatever. Or if you have other things to do, we just see each other on Friday. Okay, thanks for coming, guys. Let me just put off the recording.